start the recording whenever.
Excellent. Well, thanks for the invitation. It's really a pleasure to speak to this group. I will start off by saying I suspect that this talk will be maybe a little bit higher level and kind of policy oriented than some of the more kind of engineering heavy talks that I've seen on the docket for this group. But I nonetheless hope this will be really useful and interesting to this audience and maybe give some useful context to kind of related challenges in rapidly integrating vast amounts of solar, wind, and storage into our electric system in the United States. Just as a quick background, I'm going to be discussing, as the title says here, the status and drivers of backlogs in our generator interconnection process, or how we get new power plants or proposed power plants kind of studied and approved to connect to our electric system. Our team at Lawrence Berkeley National Lab has been compiling and analyzing these interconnection data for a number of years. And we're really seeing growing interest and I would say urgency around this work for a number of reasons. I mean, first and foremost, those of you that talk to folks in the wind and solar and storage industry might hear developers of these clean energy projects citing interconnection as one of the leading barriers to getting their projects actually completed. That's increasingly become the case. And then very recently, we're seeing reforms announced by the Federal Energy Regulatory Commission to really change the landscape of how this interconnection process works. And I'll discuss those a little bit later. But so anyway, hope this will be an interesting talk. And I look forward to the discussion at the end. So as a quick overview of what I'll share, the talk that I'll give today has basically three main components. I'll start with a quick overview of what's happening in the interconnection queues across the United States, really focusing on kind of the volume and trends of active grid interconnection requests. And then I'll share some data that provide evidence of major problems with this current interconnection process. And so that's kind of twofold. First, I'll discuss the delays and bottlenecks and the lengthening timelines we're seeing for studies to be for these interconnection studies to occur. And then I'll share some data on the increasing costs that developers and generators are facing to connect their projects to the grid. And then I'll conclude the last couple of slides by discussing some of these reforms and proposed solutions that we're hearing for the interconnection problem. Now, I suspect that most of you on this call already know what the interconnection queues are and roughly what the interconnection process looks like, but let me go ahead and give a quick background just as a refresher. In a nutshell, electric grid operators require any proposed power plant that's seeking to connect to the grid to undergo a series of studies, basically to assess and understand what's the impact of injecting this new electric capacity at a specific location on the grid. And this process is designed to establish what new equipment would be required and what's the cost of that equipment. It also assigns the cost of that equipment to the various actors and stakeholders in the interconnection process. What I'm showing on the screen now is kind of a typical or simplified outline of that interconnection study process, though I will note this is sort of the outgoing process. It's kind of what we call a serial interconnection study process in which a developer would submit an interconnection request and then go in a serial fashion through a series of studies, ultimately, ideally culminating in an interconnection agreement, which is like a contract between the balancing area and the generation owner to safely connect to the grid, and then ultimately reach commercial operation. Now, as I'll share later, most projects that go through this process ultimately withdraw at some point through this study process. But I also want to emphasize that this process is also in the midst of a major reform, and FERC is now mandating that all transmission owners conduct these studies in a cluster fashion instead of one at a time, with many projects being studied at once. And I'll get into that in a little more detail later. Now, just in terms of the data that I'm going to be sharing, we collected interconnection queue data from all 7 independent system operators, or RTOs, as well as about 35 non-ISO utilities around the United States. Those are shown on the map here, and we estimate that represents roughly 85% of the total US electric load, give or take. We did our best to collect any data that's publicly available, and most of the stats I'll show today focus on projects that are active in the interconnection queues, though we also collect data on projects that have withdrawn and projects that went through the interconnection process and ultimately reached commercial operations. And just to be clear, we're really focused on data that connect, or on projects that connect to the bulk power system, or transmission interconnections. And we're not really looking at distribution connection here or behind the meter projects per se. And I'll also just emphasize that we're looking at a snapshot through the end of 2022. This is an annually updated report, so you can expect an update to this with data through the end of 2023 in early 2024, probably around April of next year. Now, just to dive right into some of the results, let me just start by sharing this figure that illustrates the total volume in the queues over the last 20 years or so. And what you can see, I think it's pretty clear that we're seeing almost an exponential growth curve here. The annual capacity in gigawatts is shown as a solid blue line on this chart. That corresponds to the left y-axis. And the number of new requests is shown as the dashed black line that corresponds to the right y-axis. And really, you can just see just an astounding amount, astounding volume of new capacity entering these interconnection queues or requesting grid interconnection each year, with, in fact, over 700 gigawatts of new generation and storage capacity requesting connection in 2022 alone. Now, you might notice there's a slight dip in the number of new requests from 2021 to 2022. I'll discuss that a little bit more later, but I just would note here, there's a note down on the bottom that two of the largest electricity markets or grid operators in the US, the California ISO and PJM, essentially, if not explicitly, paused all new interconnection requests in the year 2022. So that's just simply due to this unprecedented volume that they saw in recent years. They just had to tap the brakes there. And so we see that reflected in these data. Now, let me just start here with one of the kind of biggest and key takeaways of the whole presentation today. As of the end of 2022, we find more than 2 terawatts of generation and storage capacity actively seeking grid interconnection across the United States. Now, I don't know about you all, but I worked in kind of electricity analysis for 10 or 12 years now, and I don't get to use the unit of terawatts all that frequently, so it's just kind of an astounding amount. In fact, it's so much, it vastly exceeds the total installed capacity of the US power plant fleet. And that's basically shown on the left-hand chart here, where you can see the installed capacity versus the active capacity in the interconnection queues, shown for both 2010 and 2022. And what you'll notice is not only the growth in the queues from 2010 to 2022, but also just the absolute fundamental shift in the type and resources of electricity generation that we're seeing proposed compared to what's currently installed. So look at the 2022 bar chart in the queues, and you see 95% or more zero carbon electricity resources. We also looked at the proposed or capacity in the queues compared to the installed capacity and peak load across the 7 RTOs in the United States. And again, you can see, we see in almost every case, substantially more capacity in the queues than the installed capacity or peak load of each of these wholesale electricity markets. Now, this chart, again, shows the total capacity in gigawatts in the queues over time as a time series from 2014 to 2022. But we've broken it out here to see a little bit more detail by generator type. So you can see each kind of pane here is a different generation type. The total height of the bar represents the full cumulative capacity in the queues as of that year. And the hatched portion represents the amount of capacity in a hybrid configuration. So it's really clear to see just absolutely explosive growth of solar and storage in the queues over time. the amount of proposed wind that we're seeing in the queues is a little bit flatter or slower growth rate, but still definitely we're seeing some growth in recent years. And it stands now at about 300 gigawatts of proposed capacity, wind capacity. Over 100 gigawatts of that is for offshore wind. And then fourth pane here, looking at natural gas. In general, we see a pretty substantial decline in the proposed capacity since 2015, currently standing at around 80 gigawatts of gas in the queues. And this next chart also looks at the active capacity in the queues as a time series from 2014 to 2022, but instead of showing the generation type across the top, I'm breaking it out by region, or the basically grid operating regions, where we have the 7 ISOs and then the non-ISO West and also the non-ISO Southeast shown here. And I'm really just focusing on kind of the predominant generator resources here. I've left out some of the kind of smaller other ones, but focusing on storage, solar, wind, and gas. And we can really see that the West just has an unbelievable amount of capacity in the queues, almost 600 gigawatts, followed by MISO and PJM. Some of these markets had just explosive growth in 2021 and or 2022. And I mentioned earlier that PJM and CAISO basically paused their interconnection requests for the year 2022. We saw just a slight growth in PJM in 2022. They indicated that they wouldn't be studying any new grid interconnection requests until 2025. So it kind of sent a signal to developers to potentially not submit requests there. And CAISO, which normally does an annual queue cluster window, postponed their 2022 window until 2023. And although we don't show these data here, I have seen the requests for CAISO for 2023, and they saw over 350 gigawatts of new generation and storage requests just in California ISO, just submitted in 2023. So it's going to be exciting to see those numbers when we compile these data next year. Now, we also produced just this series of maps to kind of illustrate that queued capacity of solar, wind, storage, and gas in each region across the US. I won't spend too much time here just for the sake of time, but you can really see proposed solar is pretty widespread, highest in the West, and we're seeing some pretty rapid growth in MISO. For wind, we see the West and maybe SPP kind of dominant. But we're definitely seeing a lot more interest in offshore wind, particularly on the East Coast and in New York ISO in particular. And for storage, we're seeing most of it proposed in the West, and certainly a lot of storage is proposed in California as well. But that's expanding pretty rapidly to other markets also. Now, the queue data also give us some indication of when these proposed projects might actually come online, if they were to do so. These proposed online dates should be taken with a grain of salt. We don't typically see them, held to that standard, and we see the actual online dates differing quite a bit from these proposed online dates. But nonetheless, we're seeing basically 62% or over 1.2 terawatts of the capacity has proposed to come online by the end of 2025. Maybe what's more interesting and perhaps more important is the status in the interconnection study process at which we find these requests. And that's shown over here on the right-hand chart. You can basically think of this in kind of a linear fashion, like that diagram I showed earlier of the interconnection study process, where, starting from the feasibility study, which is kind of one of the more initial phases, moving all the way on to actually having an executed or signed interconnection agreement. And what we found is about 13% or over 250 gigawatts of the capacity in the queues already has a signed or executed interconnection agreement. So those projects are indeed much more likely to come online than the others, perhaps. I'm going to just show a couple of slides that illustrate some trends in hybrid power plants. We're seeing definitely growing interest in proposed hybrids across this sample each year. just as an example, we're seeing 48% of all of the solar capacity in the queues is now proposed in a hybrid configuration. The vast majority of that, or about 430 gigawatts, is for solar plus storage plants. For wind, we're just seeing about 8% of wind capacity proposed as a hybrid. And you can see roughly half of the storage capacity in the queues is paired with some form of generation. Now, on the right-hand side here, again, you can kind of just see that year-over-year growth in the proposed hybrid capacity that we're seeing in the queues. So definitely more and more interest in hybrids. I think that makes sense as we're seeing increasing penetration of solar and wind, especially in certain markets, that pairing, for example, solar with storage can kind of counter the value erosion or cannibalization that you might have with an increasing penetration of solar in a specific region, and just improve the value proposition of these power plants. Now, looking across regions, this is again focusing on hybrid power plants. We've broken down the percent of proposed capacity that is in a hybrid configuration across each of these grid operating regions for the various kind of generation and storage types. I think kind of one of the key and interesting takeaways here is that we do see solar hybrids, pretty widespread in really every grid operating region across the US. But certainly highest in California ISO and the non-ISO West. You can see 97%, or essentially all of the solar in the CAISO queue is in a hybrid configuration. Again, the vast majority of that would be solar plus storage. For wind, of course, these are less common overall, and they're also more geographically concentrated in California, the West, and to some extent MISO. Now, the last, 10 or so slides, I think I've been sharing some really exciting and perhaps optimistic stats about all the clean energy capacity that we're seeing proposed and in development, and maybe we'd say early stages of development. And as exciting as it is to see this remarkable volume of clean energy capacity in the queues, I should also share the bad news or tap the brakes on that excitement a little bit. So when we studied what fraction of these proposed projects that requested grid interconnection, what fraction actually came online or reached commercial operations, we're seeing very, very low completion rates. Historically, when we look from projects that were proposed from 2000 through 2018, we saw just about 21% of those proposed projects have reached commercial operations by the end of 2022. That's by number. When we look by capacity, that rate is even lower. It's just about 14% of the proposed capacity in the queues has historically actually reached operational state. As you can see, that completion rate varies pretty widely across these regions, and the only regions we're seeing with completion rates over 30% are ISO New England and ERCOT. Now, obviously a low completion rate or high withdrawal rate doesn't sound like a good thing on the surface, but it's also can be really problematic when you think about the interconnection study process, because when these projects withdraw, it can often trigger restudies and increase the uncertainty for the projects that remain in the queue and that are still undergoing their studies. A lot of those studies are dependent, or the models utilize all of the projects existing in the queue to run those interconnection studies. So when projects withdraw, they have to rerun them. And that, of course, that increases uncertainty and delays of this whole process. So with that background and kind of now understanding what's in the queue, let me spend the next few minutes talking about what I call kind of the first evidence of a major problem in this interconnection process. And that's by looking at the timelines or the duration that we're seeing projects take to go through this study process. So we were just talking about the fraction of projects that withdraw from the queue. So let me stick with these requests that ultimately withdraw on this next slide. Overall, what we found when we looked at how long it takes to go from submitting the interconnection request to ultimately deciding to withdraw, historically, we've seen most projects basically do that in about a year. So, a median plant for quite a while, we've seen, submitting their request and then withdrawing in about 1 year. But as you can see on the chart on the left, that timeline is starting to trend upward a little bit. But I think what we're also seeing, and this is kind of evidence of the same thing, and is perhaps even more concerning, if you look at the chart on the right, again, I'm showing these various interconnection study phases across the x-axis here. And on the y-axis, it's showing the percent that withdraws in that phase for projects that were withdrawn in these various year groups, with kind of the darker shades representing more recent projects. That's probably a lot to take in, but let me just summarize the key takeaway here. It's pretty clear from this chart that we're seeing increasingly projects are waiting until later and later stages of the interconnection study process to make the decision to withdraw. Or in other words, we're seeing a higher fraction of projects waiting until the facility study or even having an executed interconnection agreement before they withdraw. Now, again, these late stage withdrawals can be particularly problematic for this whole interconnection study process. Again, necessitating restudies, disrupting assumptions built into all these study models, and overall just increasing study durations. So that's certainly a concerning trend. Now, looking at a different duration, I'm turning to the period of time from submitting an interconnection request until a project actually has a signed interconnection agreement. And you can see the median and interquartile range, has fluctuated over the years, but we're definitely seeing a pretty clear increasing trend in that duration, especially since 2015. We're seeing, a pretty strong uptick in that duration. You can kind of think of this as the bounds of the interconnection study process itself. So I think this is a really important period to study. And, it's gotten to the point where the typical or median project that signed an interconnection agreement in 2022 took about 3 years to do so from the point at which it submitted an interconnection request. So, 3 years is quite a long time to have uncertainty in a project's development cycle. So I think this is kind of a key cause for concern that, that's so long and also that it's been increasing so rapidly. Now, naturally, that duration differs across the various regions and generator types. Regions here are shown on the left, and the generator types shown on the right. I'll just highlight a couple. We're seeing kind of the longest interconnection study durations in PJM, SPP, New York, and the Mid-Continent ISO. All of those have study periods over 3 years. But we're seeing particularly short durations in ERCOT in Texas. And I just want to highlight quickly that, first of all, ERCOT, as most of you probably know, is not FERC jurisdictional. So they're kind of operating under a different process than the rest of these markets. But they also operate under what's known as a connect and manage approach, where the interconnection study process can just move a whole lot more quickly. And ultimately, the generator is not assigned with kind of deep network upgrade costs as they are in other markets. So, the evidence is pretty clear that things in ERCOT can move more quickly. And we're hearing, certainly anecdotally, from many developers that we speak with that, they prefer working in ERCOT just because it's so quick and easy in that regard. Looking at generator type, of course, there's not a huge difference here, but, in general, maybe wind plants take a little bit longer, battery plants can move through a little bit more quickly. There's also a pretty clear step change in that interconnection request to interconnection agreement duration when you compare small projects, and here I'm using small as kind of the way FERC defines it. The small generator interconnection process applies to any plant less than 20 megawatts in capacity. And a different process, the LGIP, large generator interconnection process, applies to plants greater than 20 megawatts. So it's pretty clear you see a step change in that duration for larger plants here as well. All right, now let me turn to a different duration, a different period of time that we studied. And this is looking at after a project signs their interconnection agreement, and now they're moving all the way toward commercial operation. How long does it take after you sign your agreement to actually build the project and come online? We had more limited data here, so it's hard to draw really firm conclusions, but we do see kind of a slight increasing trend over time, though I should note that's really driven by California ISO, where we see really strong outlier in terms of this duration. This process after the interconnection agreement might entail, things like getting final kind of financing for your project, securing an offtake agreement, like a power purchase agreement, securing your local special use permit or kind of other kind of environmental permitting and things like that. We've certainly heard that some local permits are in fact expiring while projects are stuck in the queue. So I think this period is also problematic. And we're hearing, actually, when we talked to CAISO about this period, they said that they have a number of projects in the queue that are kind of just languishing there, again, waiting for their offtake agreement or waiting for basically procurement. So I think that's something that really needs to be addressed, is basically better interlinkages between kind of procurement, offtake, and this whole interconnection process. All right, finally, let me turn to what we consider kind of the full duration from submitting an interconnection request all the way to becoming commercially operational. So, this is when I first submit the request to when I have a built project providing power to the grid. Again, you can see that timeline is increasing pretty steadily over the period of time we studied, with a sharp increase in 2022. In fact, for the typical or median project that came online in 2022, it took about 5 years for that project to go from the interconnection request to commercial operations. So again, very concerning timelines, obviously, really troubling and problematic for developers of these projects. Again, we looked at these trends across the different regions. We're seeing, long timelines in CAISO and New York ISO, and, shorter overall timelines, again, in ERCOT, the Southeast, and ISO New England. We also, again, kind of a similar trend for what we saw with the duration from interconnection request to interconnection agreement. We're seeing, these largest projects tend to take the longest to come online. In fact, there's a pretty clear kind of monotonic arrangement of project size to duration. Let's see. All right, so now I'm kind of moving into the second, what I would consider kind of the second big bucket of potential kind of problems or evidence of a problem in this whole interconnection process. So we collected and analyzed the cost that generators face to interconnect across 5 ISOs. I'm going to share just a couple slides on those. But just on this first chart, I think it's pretty clear to illustrate that this is just for PJM. We can see, pretty drastically increasing costs when we compare interconnection costs that were assigned or studied in earlier periods to more recent periods when we look across all projects or just projects that completed and signed an interconnection agreement, or certainly especially active and withdrawn projects. Now, looking at all 5 of these regions that we studied, MISO, SPP, PJM, New York, and ISO New England, we're seeing basically increasing interconnection costs over time in all of these regions. And I should emphasize that these increasing costs are driven, 80 or 90% or more in some cases, by what we call broader network upgrades. And these are upgrades to the transmission system beyond the point of interconnection. So certainly we'd expect, if I were to build a wind or solar power plant and I connect at a certain substation, I would be responsible for paying the upgrades to that substation, transformers, whatever's needed there at that substation. But these generators are also responsible for upgrades again, to the transmission system beyond that substation or the point of interconnection. And that's really driving these cost increases. We're seeing for projects that completed all studies and signed an interconnection agreement, overall, we're seeing, interconnection costs roughly doubling and costs increasing even more for projects that are still active in the queues, and even more so still for projects that ultimately withdrew. Now, another concerning trend here is that we're actually seeing, on average, higher interconnection costs for renewables and storage compared to natural gas interconnection requests. So we compared kind of the typical interconnection costs to what we consider a typical project capital expenditure in these different regions. And for solar, what we found is, for projects that sign interconnection agreements, the interconnection costs might encompass 5 to 10% of what you consider a total project capex. But for projects that withdraw, it was more like 20 to 40%. Similarly, for wind, completed projects, might have faced interconnection costs in the range of 3 to 16% of a total capex, whereas withdrawn wind plants range from about 10 to 40%. Again, over here on the chart on the far left, you can see the typical costs for natural gas tended to be lower than those for storage, solar, and wind. We were particularly surprised by this result for storage because one would think storage could have locational flexibility as well as operational flexibility that would mitigate perhaps, or could mitigate, the need for these costly deep network upgrades. But we weren't finding that kind of borne out in the data. And that's something that FERC did look at in this new interconnection reform that I'll address in a minute. In terms of the higher costs for renewables, our hypothesis is kind of simply that renewables tend to be located in more rural areas where perhaps the existing transmission infrastructure is a little bit less developed. And that might require costlier network upgrades for those plants compared to something like natural gas that can site their plants closer to stronger transmission systems. All right, I think I've got 9 or 10 more minutes. Let me just talk for the last few slides about what's coming ahead, what's been proposed, what are the reforms that have been enacted, and what are some potential solutions that look even kind of beyond the existing reforms that we're seeing being enacted right now. Now, we've sort of taken to calling this interconnection problem a wicked problem. Some of you may be familiar with that term, but a wicked problem is basically really multifaceted problem with lots of interdependent factors that make it seem almost impossible to solve. And I don't want to give the idea that this is an impossible problem to solve, but there are a lot of factors, a lot of stakeholders, and a lot of issues that kind of need to be studied, addressed, and improved. At the highest level, I would emphasize that we've basically been asking too much from kind of an antiquated interconnection process. So our kind of existing interconnection process was designed in 2003. That's 20 years ago now. Obviously, our electric system looked vastly different then than it does today. And we're undergoing an extraordinary and rapid transformation of our electric system. And this kind of 2003 interconnection process is just not up to the task. Because of that, we're seeing fundamental reforms of that process, and I'll discuss those more on the next slide. But in addition to that, I would say another very high level issue is that we've had very limited transmission expansion and investment in upgrades over the last decade or so. And the transmission expansion and upgrades that we are seeing are primarily focused on local reliability upgrades, as opposed to kind of longer range or interregional transmission investments that are really needed to bring these new clean energy resources to load. So we're not seeing the investment or development of the bulk electric grid. That's kind of driving potentially these high network upgrade costs that are being assigned to these generators in the queue. We're also seeing developers, I think a lot of times we place a lot of blame on the ISOs and the transmission owners and operators in this process. But, developers face some of the blame here too. We're seeing developers submit a lot of requests using the interconnection process as a tool for kind of data collection and price discovery, basically due to kind of low data and information transparency, and essentially low entry costs to get into the queue. So that, of course, has yielded this kind of dramatic increase in the number of requests we've seen in the queue. That has created workflow and workforce challenges for the transmission operators, and of course, just resulted in increasing backlogs across the board. We're also just seeing overall, a lack of standardization in the models and study processes, in the data, assumptions, very little consideration of things like grid enhancing technologies or alternative transmission technologies, and as I said, late stage withdrawal. So all of these things are leading to long delays, reliability concerns, costs about who should really pay for these deep network upgrades, and just really frustrating stakeholders and leading to, again, long delays and a barrier to new projects coming online. And I want to emphasize that this has become a vicious cycle where, because we have such a long timeline and backlog of these projects in the queue, it essentially incentivizes developers to submit more requests, not only just to get their place in line, but also because it's kind of the best and easiest way for them to learn about what the interconnection upgrade costs might be. So just 2 months ago in July, FERC, Federal Energy Regulatory Commission, issued Order 2023, which completely revamped and reformed the interconnection study process. So we were going from Order 2003, which again is what I said was the interconnection process that we were kind of operating under previously. Now, 20 years later, we have a new set of rules. On the left here, I've got just a bunch of bullets that outline kind of what's the motivation and reason or need for reform that FERC cites in this rulemaking. And they include things like, obviously that kind of increasing number of requests, the limited transmission capacity, and all of that leading to these increasing backlogs that I've illustrated with the data before. Interconnection studies have also increased in complexity. That's straining these transmission provider resources and causing workforce and workflow issues again. Across the US, we're seeing transmission capacity largely or fully utilized. So these interconnection customers are facing really high network upgrade costs. The backlog has resulted in a lot of uncertainty for interconnection customers and developers of these projects. But it's also important to note that when we have these backlogs and we can't bring new generation online, that can really create reliability issues as we need new generation to come online to serve load. As well, hindering the development of these new generation and storage projects, stifling competition in electricity markets and essentially benefiting the incumbent generators. So, what's in FERC Order 2023? I've outlined just a few of the key provisions over here on the left in kind of the purple box. And then in the green box on the right, I want to just emphasize that, we should think about Order 2023 as a baseline and not a ceiling for possible reform. So in other words, Order 2023 sets the new, set of rules that everyone needs to abide by. But in my opinion, probably not going to be sufficient in isolation to really solve the problem. And we need to think about broader, more systemic, and perhaps more creative solutions to this interconnection problem. So just a few key provisions include, like I said, moving away from a first come, first serve serial process to a first ready, first serve cluster study process, increasing deposits for developers submitting their requests, and increasing readiness criteria. Like, for example, developers now have to demonstrate that they have site control for their project before they enter the queue. More stringent rules around timeline and process, financial penalties for transmission providers if they have delays. Interestingly, the transmission providers will now have to make heat maps of available transmission capacity that are available to the public. So that might provide some information or data upfront to developers that are thinking about submitting requests. Just skipping ahead a little bit, there are also rules that enable kind of greater flexibility for storage, and in particular hybrid resources to submit interconnection requests and come online. One thing I'll note in particular is that it does require storage plants to be studied under kind of the real world operating conditions or assumptions of those storage projects, rather than studying them under kind of a worst case scenario that would yield the kind of greatest interconnection upgrade costs. And finally, it requires these transmission providers to consider a range of alternative transmission technologies, such as dynamic line ratings, advanced power flow controls, tower lifting, reconductoring, et cetera, that would be alternatives to kind of your traditional network upgrades. Now, quickly, just to highlight a couple of the possibilities beyond Order 2023 that we didn't see in those reforms that might really help this issue include kind of better linking the transmission planning process to the interconnection process, improving data transparency. There's a lot of talk these days about automation. So can we kind of improve the speed and reduce some of the workforce constraints by automating some of these interconnection studies? And then improvements to interconnection cost allocation. So for example, is it really fair that developers of these projects should pay for all of the network upgrades, or should some of those costs be socialized across load and electricity customers? So let me close by talking about another potential solution and other activities that are going on to improve the interconnection process. The Department of Energy has a really important and impactful program called the Interconnection Innovation Exchange, or I2X program. The mission is simply to enable simpler, faster, and fairer interconnection of clean energy resources without forgetting about reliability, resilience, and security of our electric grid. The I2X program is operating under a number of different pillars, and I'd encourage you all to get involved if you're interested in this problem and in seeking solutions. So we have a really robust stakeholder engagement program that involves a lot of what we're calling solution exchanges, or stakeholder kind of webinars, exchanges, and meetings. We're doing a lot with data and analytics. In fact, all of the data that I presented today was funded under the I2X program. And we're also working on a strategic roadmap, again, thinking about these longer range solutions beyond what we see in FERC Order 2023. So we are in the kind of final stages of drafting the strategic roadmap for interconnection for the bulk power system. And I want to highlight that we expect that roadmap to go out to the public as an RFI, a request for information, in the not too distant future. So we'd really welcome your comments on that draft roadmap. I'll skip over the key takeaways here. I think I've left you all with a lot of food for thought. Let me just highlight, we're seeing over 10,000 power plants seeking grid interconnection in the US as of the end of 2022. That represents over 1.3 terawatts of generation and 680 gigawatts of storage. But of course, most of that capacity will not be built. We're seeing, increasing delays, long timelines in the interconnection process. FERC has implemented these major reforms, but as I said, there's a lot of room for what I would call kind of additional, deeper, more systemic and creative reforms to really get at the root of this problem. And again, just to reemphasize or reiterate, DOE's I2X program is doing a lot of work in this area. Get involved, and certainly please check out the strategic roadmap when we come out with that pretty soon. I'll stop there for questions. My contact information is here. And thanks again for your attention and participation. And maybe I'll just take a look at the chat. So feel free to drop your questions there.
Thank you so much, Joe. Dan,